Hello, welcome to this short lesson about using matrix equations to solve systems of equations. So this is really a linear algebra at its most basic. So what I'm going to mention really quick though is that yes, using a graphing calculator can make these problems pretty easy as well when they're two-dimensional as such. And so you can see where I've already graphed the lines. I've already got my solution for x and y using a graphing calculator. However, I'm going to be approaching it a bit different really quick with a matrix equation, so that way you can do higher dimensional problems pretty easy, as long as they're in standard form like these will be today. Alright, so the first thing I'm going to do is actually make a matrix equation to represent this system. And so the first matrix will be a 2 by 2, and all I'm doing is actually getting all of these coefficients. Notice how the x's and y's are already lined up nice and pretty. So 5x minus 1y, 1x plus 3y, and so this matrix represents my coefficients. This next matrix will be a 2 by 1. It's going to represent my variables, so I've got x and y right here, equals, and I'm now going to have my coefficient matrix, which is what these equations were equal to, negative 29 and 23. So now this represents that equation. These two systems are exactly the same thing. It's just written in a different way using matrices. Now what I can do is I can solve this system as such. I can move this matrix to the other side, not by dividing it by it, but using its inverse. So I'll take xy, and it will now be equal to this 2 by 2 matrix as an inverse. So 5, negative 1, 1, 3, close the matrix inverse, that's an exponent of negative 1, times the coefficient matrix, or sorry, not the constant matrix, negative 29 and 23. This represents my answer. I can now get this inverse by using my methods I've learned by hand with finding determinant, finding inverse, and then multiply it using matrix multiplication. However, the real upside to this is it can be done in a calculator. So that's what I'm going to now do, and the calculator I'll be using is the Desmos matrix calculator. So I'm going to enter my matrices. I'm going to make this matrix A, where I'm going to type in each value and hit enter. And I'm going to enter this as matrix B, so it'll be, and I need to decrease the amount of columns. I had to change the amount of columns really quick. And I typed that in wrong, so that's a good tip. Please make sure you're proofreading your entries into your calculator. And now, I know you can't see that the best in the world. Now what I'm going to do is I'm going to hit enter. And I'm going to find the inverse of matrix A and multiply it with B. And I can actually do that in all one step. So I can do A, and I don't know if you're able to see that, but there's an inverse A to the negative 1 right here. And I'll bring this up so you can maybe see it a bit better. So A, and now I'm going to click on negative 1 for the inverse and multiply that with matrix B. And negative 4 and 9 are our answers. So the matrix XY equals negative 4, 9 is what all that simplified to in the calculator, and those are my answers. So as a coordinate, it would be x is negative 4, y is 9, and you'd be finished. Okay, so we're going to take a look at 3 more problems. This one's going to be very similar to the previous one, and then I'm going to take a look at some special situations after that. So I'm going to go ahead and set this equation up. As I did with matrices on the previous one, everything's lined up nice and pretty. I'm not pulling any tricks on y'all today where I might have x and y reversed on one of the equations. If ever there's not a variable present, make sure you use a 0 in the coefficient matrix to account for that. And then I've got my constant matrix out to the side here. Alright, now I'm set up, and now all I've got to do is move that coefficient matrix to the other side by inverting it. It's always important that this matrix is first when you're doing this. So you want your coefficient matrix first, inverted, and then multiplied by that constant matrix. And the reason why I'm using those terms, coefficient and constant, is because these values were coefficients of variables. These values are constant that they were equal to. All right, and now I'm ready to use the calculator again. Personal preference, I like to just kind of like start over completely new, so I'll usually just completely refresh the page, the web page for the calculator, and now start typing things in. I'm going to go ahead and do that. I invite you to pause the video to try to get this right on your own. Okay, so I've already gotten the matrices typed in there, so now I'm going to type in matrix A, the coefficient matrix, inverse, make sure you get that inverse pressed from right here, times matrix B. And so 0, negative 2 is my answer there. So xy equals the matrix 0, negative 2. So my x value is 0 and my y value is negative 2 as a coordinate pair. Let's go ahead and take a look at some unique situations you could see. Alright, so this problem actually presents a unique solution that's going to happen. So let's actually go ahead and see what's going on with it. I'm going to go ahead and set it up as I have been doing, and as you're probably used to, and I'd invite you to try that on your own if you pause the video to see if you can get it right. If ever they use different variables, that's totally okay. They can use whatever variables they want to. I've just been using x and y on these today. And I'm going to go ahead and write down that next step. Okay, now something interesting is going to happen here when I try typing this into the calculator. So I'm going to go ahead and do that and I'll show you. Alright, so I've already got those values typed into my calculator, and I'm going to type in A inverse times matrix B, and it's going to say error. I'm going to tap on this error. Singular matrices do not have an inverse. Matrix A cannot be inverted. Usually this is because the determinant ended up being 0 or something like that, and sure enough that's actually what happened right here. So what can we do? Well, we can actually say there is no single unique solution. Like there isn't, that's what happened on the other two problems. There is like one unique special solution for each of those. All right, well, that's not the end of the story. So what could happen is you could have like a graph and then it's the same graph on top of it. Like so they're the same line. And this would be a case where there's infinitely many solutions and you would have to look at a graph or do it by hand with like substitution and elimination to see what would make sense there, if it's that. And the other possibility is that these lines are parallel. And if that's the case, there's absolutely no solutions for this equation. So I'm going to actually graph this so we can have a little bit of closure on this to know which of the two it actually is. But if you do have this happen, it's going to be one of these two answers. So if that's all you see on multiple choice, just go with that. Alright, so I've used the Desmos graphing tool, and it's kind of tough to see, but if I zoom in, this one is the parallel line situation. So specifically, there is no solution, is what you'd actually see on multiple choice from this. But again, if the error happens, it's one of those two possibilities right here. Let's take a look at 3x3 and be done. Alright, so this is going to be a 3x3 matrix that's required because we have three variables. So really the technique is still the same though. So I'm going to go ahead and make my coefficient matrix, which is going to be the coefficients of the variables. But now there's a variable z to worry about. And fortunately everything's in a line and nothing's been mixed around and stuff like that. Most of the time when people miss these problems, it's because they missed a negative sign or they typed something in wrong. So just take your time, proofread your stuff, make sure that you've got everything typed in right. And now my variable matrix is x, y, and z. So this is really where the matrices start to shine. It's really tough to do one of these problems with a graphing calculator. That's where the matrices really come in handy. It's not impossible. You can use like this slider technique, but it's a pretty big headache. All right, so now I've got my constant matrix as well out to the right, and I'm ready to do my inverse as we have been doing. It's just on a larger scale now. So that coefficient matrix inverted times my constant matrix. And that's what I'm going to type in right now, as a matter of fact. So here we go, grabbing my calculator, refreshing the whole page. One thing I'm going to point out is that when I'm typing in a new matrix, I do have to adjust both the rows and the columns. And now I'll start typing in my entries. I'm going to pause the video while I do this part. All right, and so I've taken these two matrices and I've now entered them into my calculator. And yet again, I'm typing in A inverted times matrix B, and I'm getting my answers for X, Y, and Z, and I'll be finished. So what I've ended up with is that XYZ has to equal 316, and we could have an ordered triple where you put X first, then Y, then Z, and that's a three-dimensional coordinate right there as my answer. You can then take this even further, though I won't. You could do 4 variables, 5 variables, and that's the upside. You could really do however many variables you've got on a problem and deal with it. So that's it in its entirety. Please let me know what questions y'all have, if any. Thank y'all very much. Bye.